Okay, we're going on to 12.5. We are not doing 12.4. That's not part of our curriculum. So we're starting logarithmic functions, but before we actually call something a logarithmic function, let's go ahead and let's see why we have, or where logarithmic functions come from. So the first thing that we're going to do is we're going to graph this exponential function, which I already know that you know what it looks like. We just did it in the previous section, but we're going to do it again. So we're going to graph that first. So if we go ahead and if we graph this function, plugging in our values, well, 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. And 2 to the third is 8. So if I go ahead and if I plot those values, I'm going to have 0, 1 is here, 1, 2, 2, 4, 3, 8, negative 1, 1/2, negative 2, 1/4. This should look familiar. We just graphed this. So there is my exponential function f of x, which is 2 to the x. Okay, so now it's saying, okay, now let's go ahead and let's graph its inverse. So remember what inverses are. Inverses are functions that just have the domain and the range flipped, or the x's and the y flipped. So you can see that that's what's happening here. Instead of negative 2, 1/4, our inverse would have the point 1/4, negative 2 on it. Instead of negative 1, 1/2, we would have 1/2, negative 1. So we're just flipping the x's and the y. So there's a 1, 0. And this would be 2, 1, 4, 2, and 8, 3. So now when I graph these points, I'm going to be looking at, I'm going to do it in green, I'm going to be looking at the inverse of this exponential function. So let's go ahead and do that. I'm going to start with 1, 0. So that's going to be right here. 2, 1 is going to be right here. 1, 2, 3, 4, 2 is going to be right here. 5, 6, 7, 8, 8, 3 is going to be right here. So now I need 1/2, negative 1, 1/4, negative 2. So a couple of things you should be seeing. First of all, the original function got really, really close to the x-axis. Hopefully you're seeing that this function gets really, really close to the y-axis. So let's talk about really quickly what that means and what that means the x and the y-axis are called. For our exponential function right here, when a graph gets really, really close to an axis or a value and doesn't touch it, that's called the asymptote. Let me write that word for you. Asymptote. So in the case of this f of x, the x-axis is the asymptote. And in the case of f inverse of x, the y-axis is the asymptote. Now don't forget, and you can look here and you can see it, when we talked about inverses, we learned that if you had the graph of two inverses, that the inverses would always be symmetric with respect to this line, y equals x. So you can see that they are mirror images of each other over that line, y equals x. This is, of course, our inverse. So this function is called a logarithmic function. So what happens is when you have exponential functions, their inverses are always logarithmic functions. So now we've looked at it graphically. Let's look at it for a second algebraically. It says now find the equation of the inverse of 2 to the x. So remember when we found equations of inverses, we had a couple of steps we had to solve. The first one was replace the f of x with a y. then remember the next step, you flip the x and the y. Our next step was solve this equation for y. Now here's the tricky part. If I solve this equation for y, here is what it's going to look like. Y is equal to the log base 2 of x. And going from here to here, you're using a relationship that we're going to study on the next page that's very important for you to remember. So remember the last step we're finding functions was to replace the y then with the correct notation. So this is the equation of the inverse. Now notice when I wrote this 2, I said base 2. It's a subscript, which is the opposite of an exponent. So it's down a little bit. And you'll see that as we go ahead and we look at the typed material. So that's going to leave us to our logarithmic function definition. So if b is greater than 0 and b is not equal to 1, so it has the exact same restrictions as it did for the exponential function, then, and this is the relationship that you need to know. Highlight this. It's very important that you know this relationship because we're going to be going back and forth from this form to this form and vice versa. So y equals log base b of x is the same thing as b to the y is equal to x, or x equals b to the y. So notice that the base of the logarithm right there is the same thing as the base of the exponential, the base that's being raised to the power. The y is the actual exponent or the power. And that's true for all x greater than 0. So by our definition, this x has to be positive. And for every real number y can turn out to be anything. And by the way, these were also had to be true for our exponentials. All right, so let's practice in this chart. So the first thing we're going to do is we're going to practice changing these logarithmic equations into exponential equations. Okay, so we're going to go from one to the other. So first thing I'm going to do for each one of these is I'm going to tell you what the answer is, and then we're going to change it. And then we'll do a couple, and then we're going to see if you can come up with the answer. So I'm going to tell you that the log base 3 of 9 is equal to 2. And here's why I know that. Because the equation that is represented by this log equation, my exponential equation, would be 3 to the second is equal to 9. So you can read this as 3 to what power is equal to 9. Let's do this one. What is this going to be? 6 to what power is equal to 1? Well, there's only one power that you can raise 6 to that's going to get a 1, and that is the 0 power. So if I take this log equation and I change it to its related exponential, it would be 6 to the 0 power is equal to 1. All right, what's this going to be? 2 to what power is equal to 8? Well, it's going to be to the third power. So 2 to the third power is equal to 8 would be its related exponential equation. 4 to what power? Now, for right now, let's just put an x there. So if I change this to the related exponential equation, it would be 4 to the x power equals 1 over 16. Four to the x power equals 1 over 16. Can you figure out what x is? 4 to the negative 2 power equals 1 over 16. And finally, 8 to what power equals 2? Let's put an x there as well. So it would be 8 to the x power is equal to 2. Well, one way to do this would be to solve it as an exponential equation, or maybe you happen to see that it's actually 8 to the 1/3 power. If I just use some scrap and if I actually solve this, remember how if it's an exponential equation, we get the bases the same. So I can make both of these into a 2. So that would be 2 to the 3x equals 2 to the first. And see how if I take the exponents and set it equal to each other, I get 1/3. So there we've had practice going from a log equation to its related exponential. So again, the base of the log is the base of the exponential. The number on the right-hand side, or alone on the one side of the equal sign, is the exponent. And then this big number is on the right-hand side. You need to know these. So now let's go backwards. Well, how would I take this exponential and write it as a log? So it would be the log base, well, what's the base being raised to the exponent? That's 4, of 64 is equal to 3. I think it's actually harder to go from an exponential to a log than what we did up here, but that's maybe just me. How about this one? Log base 6 of the cube root of 6 is equal to 1/3. If I kind of go backwards like I did up above, it would be this to this power equals this, which you can see is what we have. Okay, now you should probably turn this off and do the last one by yourself and then come back. So this one would be the log base 5 of 1 over 125 is equal to, whoopsie, -3. Okay, so now let's take and use this to do some evaluation here. So if I have the log base 2 of 8, this is asking what is the log base 2 of 8? What I like to do is I like to put a little equals x there, because then I have all 3 parts that I need. Because to solve this, I'm going to change it to its related exponential equation, which would be 2 to the x power is equal to 8. Well, now 2 to what power is equal to 8? I know that that is 3. This one, again, I'm going to put a little equals x there. That helps me. So this one, if I change it to its related exponential, would be 3 to the x power is equal to 1/9. Now, if you can't do that in your head, we can go ahead and it's an exponential equation. We can get the bases the same. So this would be 3 to the x equals, what is 1/9 with a base of 3? Well, it's 1 over 3 squared. Then I would have to move that to the top. So it's actually 3 to the -2. That's 1/9. Now, since the bases are the same, the exponents are equal to one another, and I get -2. So now that's what they call evaluate. And again, I just think it's easier to make an equation out of it and put it equals x. So now we're going to do that exact same thing down here to solve these equations. So I'm going to change it to its related exponential, which would be 7 to the x power equals 1/7. Let's get the bases the same because it's now an exponential equation. 7 to the x equals, this would be 7 to the -1. Therefore, x equals -1. How about this one? Well, let's change it to its related exponential. It would be 4 to the 2nd equals x. So here it's just 4 squared, so 16 is equal to x. And finally, let's change this to its related exponential. It would be x to the 2nd equals 9. So now technically I would square root both sides and the answer would be plus and minus 3. But remember, in our definition, this base has to be positive. So we don't have the negative 3. So our solution is just x equals 3. All right, I'm going to stop this and go on to a part 2 because the video is getting kind of long.